Okay, let's say this element is there, and let's say we want to locate that element in the array. We want to just know where this element is in the array. So array A has this element. Let me print array A as it is. This array A has this particular element, and we want to know where what is the index of this element inside the array. There are several ways of doing this. One way is to find out that index is simply you call the function argwhere, for example, argwhere A is equal to -1200, and that will return a 2D array. And if you just want any one index, then you return that kind of thing. So if you write this thing, you will get the index exactly of the element that is there. So the index is 3. If you want to change that value, for example, the value should be 3 here. If you want to change that value, what you can do is you can write okay, A idx is equal to 3, and A is reversed to its position wherever it was created. Okay, great. Now let's play with two-dimensional indices. Let's say two-dimensional arrays. Let's say we have A equals np dot random dot rand. Let's say we have 5 by 4 matrix. Let's say a two-dimensional array. Let's round all the values by multiplying them to 10. What it does is, because all the values, this rand function, all the values it generates are the values between 0 and 1. What this multiplied by 10, what it does is it actually scales up all the values to 10, and then round function actually rounds the values to the integers. Now A will be what's the problem? Round method is no longer there. Okay, maybe there is np dot round. Maybe that np dot round, maybe np dot round is there. Yes, np dot round. So round function of np. So this A is this array, for example. That's a 5 by 4 array, 5 rows and 4 columns. So let's say I want to access the second row. First of all, let's say I want to access this particular entry. This particular entry is second row and third column, which means the index is 1, 2, because second row means the row first has index 0, row 2 has index 1. Similarly, column 1 has index 0, column 2 has index 1, and column 3 has index 2. So that is what this particular entry is. What if we want to access the whole second row? For example, we want the second row, so that's how you slice. A normal meaning of this is the row should be 1 and the columns all the columns. So that's how you access the whole second row. If you want to, for example, access the whole third row, for example, or whole second column, let's say, that means you say this, okay, the column number second and all the rows, which means the whole second column that is accessed. And that, if you see, that's the whole second column, 6, 4, 2, 10 and 1. That's what the second column is. Further, once you have you can for example access a submatrix. Let's say you want row number 1 to row number 3, not including 3, and then of these rows you want column number 2 to column number 4, let's say. And if you do that, you access the whole submatrix. First, it actually picks row number 2 and row number 3, because row number 2 starts from 1, and then of those rows it picks these columns, and you can just pick the submatrix inside. You can do a lot of processing on these matrices. For example, this is matrix A. If you just type A dot transpose, that T is for transpose, the matrix just is taken transpose of it. Further, there is a complete library, linear algebra library in NumPy. For example, if you just import NumPy dot linear algebra as LA, for example, then this linear algebra library in NumPy has a lot of functions: eigenvalues, Cholesky decomposition, computing determinant of a matrix, finding out inverse of a matrix, and whatnot. For example, let's say we have LA dot inverse, and here is np dot random dot rand, let's say some 3x3 matrix. So what it returns is, it returns the inverse of this matrix. And this linear algebra library, and there are other libraries as well, but this is one scientific library that maybe most of data science experts who actually want to do research, they might be thinking this linear algebra library that specifies a lot of functions related to these matrices or two-dimensional arrays. So that is there. Okay, so that's about indexing. We can play with these indices a lot if we want. One more thing, just one last thing. Let's say this is our A, and what we want to do is, let's say we want to sort this A with respect to the columns. We want each column to be sorted individually. What we can do is we can call sort function, and we can pass x is equals 0. X is equals 0. That means sort all the columns individually, and the result will be, if you see the result will be every column is sorted individually. If we want to sort, for example, every row individually, we will say, okay, sort x is equals 1, and every row will be sorted individually. And if this is a multi-dimensional array, more than 2 dimensions, then x's can be 2, x's can be 3. So with respect to whatever x's you want your sorting can happen, it can do that. If A is one-dimensional array, then dot sort function without an x's just sorts the one-dimensional array from beginning to the end. And if you want a descending order sort, just sort it first and then reverse it using indexing. Great. I mean, there is a lot to discuss. I'm ending this slicing here. In the next video, I'm going to show you kind of masking, or sometimes called the fancy indexing, that is much more powerful and useful in a lot of different contexts. So hope to see you in the next video with more NumPy indexing.